quantization of the free scalar field. So as we have already seen, a free scalar field can be described by the Lagrangian, where L is equal to the volume integral in a real space x times script L, where script L is equal to 1/2 the derivative of phi times the contravariant derivative of phi minus 1/2 m squared phi squared, which is equal to 1/2 phi dot squared minus 1/2 the gradient of phi times the gradient of phi minus 1/2 m squared phi squared. Now, our goal is to quantize this theory in the sense of developing a quantum theory which corresponds to the classical theory described by the above Lagrangian. So here we'll use the method of canonical quantization, which I assume is already familiar to you in the context of quantum mechanics. Specifically, suppose we were given a Lagrangian with a discrete number of dynamical variables q sub I, such that L is equal to L of q sub I, q dot sub I, and t. The canonical momenta would then be defined by p sub I, right? Defined by the partial derivative of L with respect to q dot sub I, and the Hamiltonian h would be given as, excuse me, the sum over all I times p sub I q dot sub I minus L. Now, quantum theory corresponding to this classical theory could then be constructed by promoting each p sub I and q sub I to an operator on a Hilbert space, and insisting on the canonical commutation relations. The commutator of q sub I and p sub j is equal to I h bar delta sub I j. I h t over h bar with a ket of phi 0, right? And this equation leads naturally to the Heisenberg picture description, in which the physical states are treated as independent of time, and all the time dependence is incorporated to the evolution of the operators, such that operator O as a function of time is equal to e to the I h t over h bar operator O, e to the minus I h t over h bar. To quantize the classical field theory of equation 1 and 2, we can begin by quantizing a lattice version of the theory. That is, we can replace the continuous space with a cubic lattice of closely spaced grid points with the lattice spacing A, and we can truncate the space to a finite region. The system then reduces to 1 with a discrete number of dynamical variables, exactly like the systems which we already know how to quantize. And then if we can take the limit as the lattice spacing A approaches 0 and the volume approaches infinity, the quantization of the field theory can be completed. We will see later that the A approaches 0 limit will be problematic for interacting theories, but we will see here that the program can be carried out easily for the free theory. So when we replace the continuous space with a finite lattice of points, we can label each lattice site with an index k. And in a fully detailed lattice description, we would probably label each lattice site with a triplet of integers representing the x, y, and z coordinates of the site. But for present purposes, we can imagine simply numbering each lattice site from 1 to n, where n is the total number of sites. The field operator, by the position vector x and t, is then replaced by a collection of dynamical variables, phi sub k of t, where one can think of phi sub k of t as representing the average value of phi of the position vector x and t in a cube of size a surrounding the lattice site k. So the continuum canonical momentum density, pi of the position vector x and t, is equal to the partial derivative of script L with respect to phi dot of the position vector x and t, which is equal to phi dot of the position vector x and t. And the Hamiltonian h is equal to the volume integral in a real space x times the quantity pi dot minus script L. The trivial canonical commutation relations carry over trivially, such that the commutator of phi of the position vector x prime in t and phi of the position vector x in t is equal to 0, and the commutator of pi of the position vector x prime in t and pi of the position vector x in t is equal to 0, obviously. Now for the non-trivial canonical commutation relation, the result will be clearest if we first rewrite the last equation in line 19 as a sum, which will become an integral in the limit. So if we let script r denote a region in the lattice, the sum over all k as an element within the region script R of the commutator of phi sub k prime and pi sub k times delta v is equal to I h bar times the sum over all k as an element within the region script R of delta sub k prime k, which is equal to I h bar and 1 if k prime exists within the region script R and 0 otherwise. The commutators of h, the Hamiltonian with the creation and annihilation operators, are the commutator of h and a dagger is equal to h bar omega a dagger, and the commutator of h and a is equal to minus h bar omega a, from which it follows that the result of applying a dagger to an eigenstate of h is to produce an eigenstate of h with an eigenvalue higher than the original by h bar omega, while a acts on an eigenstate of h to lower the eigenvalue by h bar omega. The ground state of h therefore satisfies a acting on the 0 vector is equal to 0, while the normalized and decided state can be written as the n ket is equal to 1 over the square root of n factorial times a dagger to the nth power times the n ket, where the eigenvalue, the energy, is E sub n equal to this quantity n plus 1/2